So questions from homework 4, if you got them.
So homework 4?
Yeah. Megan, are you 11? Okay. So typically I would start a problem like this with a prime factorization, but I actually noticed something that'll make life even easier right here, is that both of these have the same base for their exponential. So I can just start by multiplying them together directly and just adding their exponents. And now I'm going to do my prime factorization. So 64 is 2 to the 6th. And 4 is 2 squared. And when I do an exponent of an exponent, I need to multiply the exponents. So 6 times 7/9 becomes 7/3. 14 thirds. And 2 times 3/4 becomes 3/2. I reduced as I multiplied, just if you were wondering, like, wait a minute, that's not what I get. Well, I reduced after I multiplied, right? And then since these have the same base now, they're both base 2, I can do this division by subtracting their exponents. To subtract those exponents, I need to make a common denominator. In this case, it should be pretty easy to see that common denominator should be 6. So the first fraction I'll multiply by 2 over 2, and the second fraction I'll multiply by 3 over 3. That gives me 2 to the 28 over 6 minus 9 over 6, which gives me 2 to the 19 over 6. And now that I have all my like terms combined, I'm going to use my definition for the exponential form and rewrite this as a radical. But I notice when I do that the exponent on my radical is bigger than my index. So I know I can still reduce this radical. So I'm going to break up 2 to the 19th into packets of 6. So 6 plus 6 plus 6 is 18. And that'll leave one more 2 left over. So I can make 3 packets of 6. Then I have 1 left over. So each one of these 2's can come out front. I have this stuff left underneath. So I have 2 times 2 times 2 times the 6th root of 2 to the 1st, or just 8 times the 6th root of 2 to the 1st.
It's probably a good idea to get those exponent things to memory.
Those exponent properties, yeah, you'll use them a ton when doing this assignment and the next one, and they're ones that don't apply just to this chapter, but those are rules that we'll use rather frequently going forward. And they're, of the second semester things that we'll do, maybe the most important thing going forward is to have those exponent rules at least functionally, so you can use them without having to think about it too hard. Just like factoring was maybe the key first semester skill, kind of moving forward, that these exponent rules are probably your key second semester skill moving forward. Joe?
Can we do number 9 or 10, whatever you think is more challenging?
Sure. Megan, are you good to move forward? Okay. Were you happy with what we did there? Okay. Did you have it most of the way? Some of the way? Part of the way? How far did you get, or did you understand? Are you good?
I feel like I'm better.
Okay. Well, I'll tell you what, Joe, you said 9 or 10.
Yeah, whatever one you think.
10 is massively easier if you look at it the right way.
Oh, that's true, because you have 12 and 2, right?
No. It's because this 5 is going to get rid of the fractional exponent here.
Okay.
I can get rid of the fractions on the very first step. So if I use the property 2, which is the exponent of a product, I can do that. And then if I use my property 3, which is the exponent of an exponent, I multiply the exponents together, so I just get 12 to the third times 8 to the third. And I just type that stuff in my calculator and get some big whopper of a number, but I'm done.
So you were able to do that because the 5 outside of the parentheses had the same value as the 3/5.
As the denominator, and as it basically is going to get rid of all the fractional exponents for me, so I didn't even have to worry about doing a prime factorization there.
Oh, okay.
Which
That's neat.
is kind of nice when you notice that. Now, you could have certainly approached this the same way we did the previous one and like done the prime factorization, really kind of work from the outside in. But it looked to me like I saw that shortcut where I'm like, oh, this can be pretty easy.
Oh, that's good.
Megan?
So the 5 or
Yeah, when you multiply 5 times 3/5, you just get 3.
Oh.
Right? 3/5 times 5/1 is just 3.
Oh.
Is that cool? So that problem becomes pretty manageable if we think about it that way. 9 is a bit more difficult because, well, right away I can see that I'm going to have issues because the 16 and 5 don't have any like factors going on. So this will be a little bit more difficult because it'll just get a little messier to keep track of. So I could, let's see, what's going to be the best place to start? I think I'm going to start by just kind of doing the same thing we did in the previous problem, which was doing this. If you started with a prime factorization, though, that would either. At some point, you're going to have to do that. Just a little bit less writing, I think, to do this as my first set of steps. Okay with that? And then exponent of an exponent, that'll be -5/3, and then that'll be -7/3. Right? Exponent of an exponent, I'm multiplying, so I reduced as I multiplied. And now I'm going to do my prime factorization. So that's going to be 2 to the 4th is 16. So that's going to be 2 to the -20/3. Still times 5 to the -7/3.
Before you continue, can I ask a question?
Sure, go ahead.
So you got the 2 to the 4th because obviously 16, when you do prime factorization, that's what you get.
Yes.
And then the exponents above that, where did you get those exponents?
The -5/3.
Yeah.
Already on the outside of the 16.
Okay.
So it just comes along for the ride.
Okay.
Okay. Still everybody's doing okay? Where we're at here? So now I'm going to get rid of the negative exponent. Okay. And I'm going to now convert these exponential forms into radical forms. Okay. So I notice here that the exponent is bigger than my index, so I'm going to try to break this up. So I'm going to put these into packets of 3. So that's 6 packets of 3, that's 18. Then I have 2 left over, right? And I'm going to do the same thing here on the 5. I can get 2 packets of 3 and then 1 left over. So that's going to give me 2 times, well, I'm going to just write it as 2 to the 6th here. Oops. 1 over 2 to the 6th times cube root 2 squared times 5 squared times cube root 5 to the 1st. Okay, there. Now my issue is that I still have these radicals in the denominator though, right? To reduce them, but I didn't get it reduced all the way. So if I look at the cube root of 2 squared, I need to have 3 2's under that cube root to get rid of it. Currently I have 1 2. So I'll multiply 1 more cube root of 2. That'll get me to 3 cube roots of 2 in the denominator. Cool there. And then with the more, so that's going to give me cube root 5 over 2 to the 6th times
Mr. Blue,
yes.
you did the stuff in blue and green because you needed to cancel out the cube root, correct?
Correct. So the goal is one of the things we've agreed on as mathematicians is that we're not going to leave a denominator of our fraction.
Right.
So that's the blue and green was me getting rid of those 2 radicals. Yes.
Okay. Why not?
Megan? Well, multiplying by a square root isn't going to cancel or help me cancel the cube root, right? We can multiply a square root to the top and bottom, but then we'd have to go and do like change the exponents or change into exponential form and add the exponents and do all that mumbo jumbo, and you'll still be left with like, you know, something or another that's probably not going to reduce out to just be regular. Is that? So the radical really needs to match whatever the radical is you're trying to reduce. Is that okay? So just to refresh our memories on what we did last time, of representing a radical called the exponential form. I presented you with these 7 properties for exponents that we'll use kind of work around having different kinds of radicals. By converting them into the exponential form, I then get access to all these properties of exponents that I can use. So if I multiply 2 like exponentials with the same base, I add their exponents and the base stays the same. If I have the exponent of a product, that exponent applies to both factors of the product. If I have an exponent of an exponent, the exponents multiply and the base stays the same. if I have the quotient of two like exponents, the base stays the same and I subtract the exponents. If I have the exponent of a fraction, that exponent applies to both the numerator and denominator of the fraction. If I have any non-zero number to the 0, that's just 1. And if I have a negative exponent, that makes a reciprocal. So let's just a couple of kind of using these exponent methodologies here, and then we'll release you guys to work on this homework 5, or if you still have homework 4 stuff to finish up, you could do either one, although I would probably recommend doing the homework 5 part first if you haven't done homework 4. I saw. Yeah, that's some luck right there, my friend. Okay, so this first problem, I see that I have unlike radicals, right? I have a square root, cube root, and a fourth root. So I know I need to convert those into exponential form at some point. Probably before I do that, though, what I would do, I noticed the 4, 8, and 32 aren't primes. So I'm going to do a prime factorization, and then I'll convert them into exponential form. So 8 is 2 to the third. 4 is 2 squared to the fifth. Now I remember, even though there's no index written there, that I understand the index to be 2. So when I convert this into form, this is 2 to the 3 halves. And the next one is 2 to the 2 thirds. And the last one is 2 to the 5 fourths. And I acknowledge that, you know, each of these radicals I could reduce at this step. You could do that now. It's fine. I'm just going to wait till the very end, because as I combine these things together, it's likely I'd have to reduce my radical again. So I'm going to try to do all my reducing just at one place rather than have to do it a bunch of times along the way. Everybody okay with that plan? Okay. So again, if you wanted to do it there, it wouldn't be wrong. It just, you might have to still do it, reduce a radical again later. I'm just going to wait and do my reducing all in one place rather than doing it like a couple of times throughout the problem. But either way of doing it is fine. It's not going to make it wrong. Okay. So what I have here is like a property 1 situation, right? Because each of these exponentials has the same base. That base is 2. I can multiply them together just by adding the exponents. So I have 2 to the 3 halves plus 2 thirds plus 5 fourths. To add those fractions, I need to have a common denominator. So in this situation, like any common denominator is going to be fine. Like the least common denominator doesn't save you an extraordinary amount of work or make the problem kind of intractable if you don't use a least common denominator, but it's still like is the easiest way to do it. But if you're just like, I don't know what the least common denominator is, and you just multiply all the denominators together and call that what you're going to use, that's going to work. You might have to do a little bit of reducing, but the reducing for fractions is pretty easy and compared to some of the other things we had been doing. So again, if you don't find the least common denominator, it's not going to, you know, like make the problem now somehow like so hard that it's kind of not possible for us. So here the least common denominator is just going to be 12. So I'll multiply that first fraction by 6 over 6, the next fraction by 4 over 4, and the last fraction by 3 over 3. Is it okay that I'm just kind of using this like goofy notation here to show you what I'm multiplying by? Is everybody cool with what I mean there? It's just neater than trying to like sneak in the fractions on the side or whatever. So that's going to be 18 over 12 plus 8 over 12 plus 15 over 12. And when I add those together, 18 and 8 is 26, and then 15 more is 41. So if I think about that, that'd be the 12th root of 2 to the 41. I notice that my exponent is bigger than my index, so I'm going to package these together in packets of 12. So 3 12s is 36. That leaves me 5 left over. Everybody's okay there? So I can take out 1, 2, 3 2s, and then I'll still have the 2 to the 5th left underneath. And then if I just simplify everything down, 2 times 2 times 2 is 8. And 2 to the 5th is 32. And that's as good as we can do there.
Can you go a little bit to the left? I just want to see a step real quick. Can you go a little bit to the low? Yes. Okay, I see what you did. I was confused about the 2, but now I see it.
Okay. Okay. Questions on this example before I move to the next one? Megan? The only property I used was at this step, I used property 1 when I multiplied those exponentials together. Everything after that was either using the definition or just like basic arithmetic stuff. Let's do another. This one will be a little bit more challenging. Again, if I look at this, there's nothing obvious that I can do with a property to shorten this up or combine any like term right here, because all of the bases are different. I can't do anything to combine them that way, and all the exponents are different. So there's no good shortcut here. So I'm just going to start by doing a prime factorization for each of the bases. So 6 is 2 times 3. 8 is 2 to the 3rd. And 12 is 2 squared times 3. And I'm going to put an exponent of 1 on all those things, just for clarity's sake for you guys. So far, so good? So that was just me doing a prime factorization. Now, when I look at these two, that looks like property 2 to me, where I have the exponent of a product. So property 2 says I can take that exponent and apply it to each factor of my product. And then that 2 to the 3rd to the negative 5/4 I'm not doing anything with right this second. So again, I use property 2 there. And there's nothing magic about the numbering that I made for those properties. I just wrote them down in some order that seemed, I don't know, was like the way that I wanted to write them down. So I'd remember them in which order. But like, there's nothing magic about the order that I wrote them. So, okay. Now what I want to do is I want to get rid of the the parentheses in each of these 3 situations. So that's going to be dictated by property 3, the exponent of an exponent. So the exponent of an exponent I multiply. So 1 times 2/3 is 2/3. 1 times 2/3 is 2/3. 3 times -5/4 is -15/4. 2 times 7/9 is 14/9. And 1 times 7/9 is still just 7/9.
So basically, you just multiply the exponent inside the parentheses by the
Exponent outside the parentheses. Yep. So if I have an exponent of an exponent like that, they just multiply together. And since all the exponents inside were integers, it was pretty easy to do that multiplication. It was no big deal. So what I'm going to do now is I'm going to combine my like terms. So the 2's in the numerator are being multiplied together, so I can add their exponents. Actually, we won't have any fraction when we're done here.
Do we need to find the least common denominator?
We will, but I'm going to do a little bit more than just that here.
Okay.
And then we have this 2 in the denominator, which is also a like term, right? So I can subtract that exponent. So this I used property 1 and also property 4. The 3's are also like terms. So using property 4, I can combine those together by subtracting their exponents. Is everybody okay there? So now I'm going to make a least common denominator for each of these 2 addition and subtraction problems. So in the first problem, my denominators are 3, 4, and 9. The least common denominator there is going to be 36. So I need to multiply the first fraction by 12, second fraction by 9, and the last fraction by 4. In the second problem, my denominators are 3 and 9, so my least common denominator is going to be 9. Multiply the first fraction by 3, and the second fraction, I don't have to multiply it by anything because its denominator is already 9. So I'll write a 1 there, but that's the same as doing nothing at all, right? So when I do that, I have 2 to the 24/36 minus 135 over 36 minus 56 over 36 times 6 over 9 minus 7 over 9. Is everybody okay to there? So that's going to give me 2 to the negative 167 over 36 times 3 to the negative 1/9. Everybody okay there? So now I've combined all the like terms that I can, right? I can't combine the 2 and the 3 because their bases are different and their exponents are different. So I'm going to apply my property for negative exponents. I think I listed that as property 7. And then I'm going to convert these back into radical forms. I notice here that I should be able to reduce that radical because 167 is bigger than 36. So how many times does 36 go into 167? 4 times. And then I have 23 left over. So I can take out 1, 2, 3, 4 2's. And I'm left with 2 to the 3. So now my radicals are all reduced. The last thing that I'm going to worry about now is the radicals in my denominator. Oh, excuse me. So if I look here, I have 2 to the 23rd. That's a 6th root. I need 13 more 2's to cancel out that 36th root. Everybody agree with that? So we'll multiply the top and bottom by the 36th root of 2 to the 13th. And if I look at the 9th root of 3 to the 1st, I'm going to need 8 more 3's to cancel that. So the 9th root of 3 to the 8th.
Are you canceling out or are you getting rid of the
radical? Yes, that's exactly what we're doing. So I'm going to have 2 to the 4th now times the 36th root of 2 to the 36th and the 9th root of 3 to the 9th. Oops. My numerator, I have this new stuff, though. Almost forgot to write that down. So the 36th root of 2 to the 36 is just 2. And the 9th root of 3 to the 9th is just 3. So my denominator, I have 2 to the 5th times 3, which is 96. And then if you want to, I can do 2 to the 13th on my calculator. That's 8192. And I can do 3 to the 9th on my calculator. That's, 3 to the 8th on my calculator. That's 6561. If you left those radicals in exponential form, though, I wouldn't mark it wrong or whatever, but that's the way I'm going to write my final answer.
See, it's hard, but it's not that bad if you just stay organized.
Yes, it's definitely one of those things, like if you don't try to do too much at once, and you're like, I just got to, combine this, I can do this, so let me do that, and then write it down. Okay, what can I do now? And I can do this, and do it, and write it down. And if you try to do like, I can do this, and this, and this, and this all at once, and try to like make up your own rule or do like 3 rules at once, mistakes happen. But if you just kind of go slow and go one step at a time, they're not so bad. And these examples that I've given you are like on the hard side. These are what I would call hard problems. They're not supposed to be easy problems or easy versions of this. So homework 5, what we're going to spend some time here today. I think one of the hardest things from you guys and kind of listening to your questions and talking to you guys over the last couple of days is kind of knowing where to stop. So what I've done here in homework 5 is I've given you the start that's in black and the end, which is in red, and your goal is to kind of fill the work in between. So you know what the answer is, you know where you're going to. It's just about kind of filling in the work in between to kind of verify that what I've written down is true. And I think this will be really, I think, a useful assignment for you to kind of build some confidence in like doing the problems in homework 4 that are, I think, more difficult because you don't necessarily know what the stopping place looks like. Joe?
So you know how we're going on like almost a 2.5 week break?
Yeah.
Like tomorrow?
Yeah.
Do you have, all your lectures are on PowerSchool?
Yes.
Because I already know, like, if I don't look at it, I'm gonna forget. And then
Yes.
when the test comes out, definitely fail again. So you can just go to PowerSchool and like look at them?
Yeah, so if you wanted to look at the previous things that we've done in class, or even what we're doing, if you go to PowerSchool, if it wants to load, right now it's going to be difficult because I have streaming the Zoom call and recording at the same time and have OneNote open and just the computer's like, you're doing too much. And God forbid I have a browser open, or Google Chrome just as a resource suck as well. It's a black hole of page, which is where I'm at. And we look under, like the Chapter 6 tab. Now my view looks a little bit different because I have a different tab for each hour. Keep specific lectures organized or whatever. But if I look at the Chapter 6 tab, it's going to go here in a second after it finishes loading this page, apparently.
Those videos are helpful.
Yeah.
Last task gave us a little retake before watching, kind of over the review over the weekend.
Yeah, I imagine so. And that's one of the reasons why I, try to record as much as I can. And like sometimes there's technical failures and it just doesn't, I can't get it to work. Like you go and there's just the link to the YouTube video. Description's pretty vague, like homework questions. I don't tell you which homework. It's just taking a while to load here or whatever, but YouTube link to the video.
Okay.
Unfortunately, the utility in PowerSchool where I would embed the video is broken right now, so I have to just like link to it in YouTube or whatever, but it's fine. It's not a big deal.
Well, that looks good. Thank you.
Yeah, no problem. Okay. So the rest of our time today, we're going to spend just kind of working on this homework 5.